This video demonstrates an end-to-end workflow for a fluid flow problem in ANSYS Fluent using Fluent's meshing mode, solution mode, and post-processing tools. I have started Fluent in a meshing mode by selecting meshing mode in the Fluent launcher. To begin, I'll import a CAD file into Fluent Meshing. I'll use the Fluent Meshing CAD import capability and import an STP file of an exhaust manifold. I'll specify that my geometry is in millimeters and confirm appropriate basic size settings. Once the CAD file is imported, Fluent Meshing creates a mesh object, which I can display. Here's the geometry of the manifold with 4 inlets and 1 outlet. In order to extract the flow volume, I need to cap these inlets and outlet. I can select a single face and use the patch options to easily patch the outlet. I'll do the same on the inlets. In Fluent Meshing, I can select a single face and patch all 4 inlets at once. Now that the openings are capped, I can proceed to extract the flow volume for my simulation. First, I need to create the fluid material point to specify that the interior volume is a fluid. To do that, I'll name it Fluid, then select 2 nodes. And Fluent Meshing will calculate the location of the material point between the selected 2 nodes. I can quickly preview to make sure that the point is in the right place. Now I can compute the flow volume. At this point, I'm ready to proceed to meshing. I'll use the auto mesh functionality in Fluent Meshing. I'll discard the solid cell zone corresponding to the manifold because I'm only interested in the flow. I'll set up prism layers to resolve the boundary layer. And I'll use the native polyhedral meshing in Fluent Meshing. The Merge Cell Zones option prevents a separate zone from being created for the prism cells. Once the mesh is generated, I can preview it. By looking at the external boundaries, I can see that nice polyhedral elements have been created. I'll save the mesh file and then change to the solver mode in Fluent by clicking the Switch to Solution button. Fluent assumes meters for all length units. I'll select millimeters to scale the mesh. After scaling, I'll redisplay the mesh to make sure that everything looks as intended. The flow is steady state. I'll use the default material, which is air. Now I'll enable the turbulence model. I'll use the standard K-epsilon model for my simulation. I'll also need to set boundary conditions. I can group these by type to make it easy to find the boundary that I'm interested in. I'll set the conditions on one of the inlets. I'll specify an inlet velocity of 10 meters per second and a moderate turbulent intensity at the inlet. I'm going to use the same settings for each of the inlets, so I'll copy them from the first inlet to the other 3. For the outlet, I just want to make sure that if any flow recirculation occurs, the settings for the flow coming back into the domain are sensible, so I'll specify the same turbulent intensity at the outlet as at the inlets. Now that the boundary conditions are established, I'm ready to solve. But first I'm going to create a few quantities to monitor during the simulation using the Fluent Report Definitions capability. I'll create a report definition to monitor the velocity on a point at the outlet. This will be a good indicator of when the flow is stabilized completely. I'll create a point surface by clicking the location with the mouse. I'll enable plotting and printing to the console as the solution progresses so that I can watch it. I'll create another report definition to monitor the mass balance in the simulation, which is a good indicator of whether the simulation is proceeding well. To do that, I'll create 2 report definitions, one for the mass flowing into the domain, and another for the net mass flow through all boundaries. Then I can create an expression for the ratio, which will represent the mass imbalance as a fraction of the total mass flowing into the domain. I'll plot the expression during the simulation. Now I'm ready to start the calculation. I'll initialize the flow field using the hybrid initialization, which will give a relatively good initial guess of the solution. Then I'll run the simulation for up to 500 iterations or until the residuals have converged. You can see the expression being plotted, which is the mass imbalance, and it should trend very close to 0. You can also see the point velocity gradually changing as the solution proceeds. The solution has now converged, and I can post-process the results. I'll plot path lines showing the flow from the inlets to the outlet. I'll plot only every fifth path line to keep the display from being too cluttered. I'll color them by the residence time, which will make it easy to spot any flow recirculation. I can add a contextual geometry to my plot. I can also look at the contours of the velocity at the outlet to see how uniform the flow is. By turning off the node values, I can plot the actual results of each cell, which will make it easier to see. You can tell that there is quite a bit of separation around the inside of the bend. At this point, I could continue by using Fluent's Adjoint Design Tool or Mesh Morpher Optimizer to modify the shape of the manifold in order to optimize quantities such as the pressure drop between the inlets and the outlet and the flow uniformity at the outlet. This concludes the demonstration of an end-to-end fluid flow simulation in ANSYS Fluent.